Okay, so what we're going to do at this point is we're basically going to derive the equations of motion for both constant acceleration and constant velocity. That's effectively the two basic types of motion that we'll deal with. Now you'll see that this is the process that we're going to use is robust enough that we could use it for any type of motion. We would just be stuck needing to deal with an integral. So let's start by assuming constant acceleration. So we're going to let AX be some constant value. And then we know that this derivative is sort of our definition of what the x component of the acceleration is. And so what we're going to do is we're basically going to say, well, let's just rearrange this so that we've got one differential on one side and a differential with respect to time on the other. Well, to undo differentials, we know that we have to take integrals. And so when I take the integral of the left-hand side, basically this is just the integral of dvx, so that's just going to give me vx. On the right-hand side, well, I've got ax. That since that is constant, right? That was my assumption that we've got a constant acceleration. I can pull that out of the integral, and then I'm left with just the integral of dt, which just gives me t. And so once I've sort of done the integral, I've got this equation that says vx equals axt plus some constant. And I know to deal with this constant, what I need to do is basically deal with initial conditions. And so at t equals 0, the velocity in the x direction is just the initial velocity, so the x component of the initial velocity. So what I'm going to do is come back and take my equation and basically plug in v naught x for my v value, 0 for my time. And so when I do that, I get v naught x equals, well, this just gives me 0 plus c. So this tells me that my constant sitting here in this equation is just the initial velocity x component. And so all I'm going to do is rewrite this where I've put that term first and then the axt second. And so this effectively gives me an equation to solve for the x component of velocity at any instant in time, as long as I know what the initial component of the velocity is. All right, well, let's keep on going. So again, I know that the x component of velocity is related to a derivative of the x component of the position with respect to time. So again, I can rearrange this equation. So I've got my position differential over here, my time differential over here, and now I can plug in that function that I have for the velocity at any point in time in the x direction. So what I've got is this larger equation, and basically what I'm going to do is I'm going to distribute the dt, and so I'm going to be left with two terms. Again, I need to integrate both sides. On the left-hand side of the equation, again, I've just got the integral of dx. That's just going to be x. And then I've got two terms on the right-hand side. The first one, well, let's see, v naught x, that's just a constant. That was our initial velocity value. That leaves me with just an integral of dt. So when I undo that integral, again, I'm just going to get v naught x times time. And then with my second term, again, ax is a constant, and so I'm left with the integral of t dt, and I know that happens to be 1/2 t squared, and so we just put the ax back in the middle. So what I've got is this equation, that the x position as a function of time is equal to the initial velocity times time, plus 1/2 times the acceleration times time squared, plus this constant. So again, I need to deal with this constant by looking at t equals 0. Well, at t equals 0, the position of my object is just x naught, right? So whatever the initial position is with the x component in the initial position. So again, when I go plug all this in, I plug in x naught for x, I plug in 0 for t, I solve, and sure enough, it leaves me with just this constant is equal to the initial position. So I come back, plug that in, and now here is my equation for the position as a function of time in x. There we go. All right, so I've got a position as a function of time, I've got a velocity as a function of time, but both of those were dependent on assuming that the acceleration was constant. Now, oddly enough, if you take those two functions, solve one for t, plug it into the other, you get this expression. So you can get final velocity squared equals, this should be the initial velocity squared, plus 2 times the acceleration dotted in with the displacement. We'll come back and talk about what dot product is between two vectors. But the important thing is that I've got 3 equations. Well, they're all vector equations, and so I know really what this means is I've got 1 equation per dimension for each of these. So that means that there is a set of 3 equations in the x direction that look like this. So if I have constant accelerated motion in the x direction, these 3 equations I can use to describe it. If I've got constant accelerated motion in the y direction, so ay is a constant, these 3 equations I can use to describe it. And if I've got constant accelerated motion in the z direction, then again, these 3 equations I can use to describe it. So part of what we're going to end up paying attention to is basically, well, is there constant acceleration in a particular direction? So is the x component, y component, z component of the acceleration, are any of those constant? If the answer is yes, then I have a set of equations that I can use in that dimension. So let's come back to think about our x equations again. And let's basically say, well, what happens if I've got constant velocity? Well, I know if I've got constant velocity, that means the velocity isn't changing, which tells me that the acceleration is 0. So I can take my equations and plug in 0 for the value for the acceleration. And again, as long as I held the acceleration constant at 0, this is okay. And so what I've got then is my velocity function basically simplifies to just tell me that the velocity at any point in time is simply the same as the initial velocity. So again, since it's constant velocity, this makes sense because it's just telling me that the velocity value isn't changing. My position equation, well again, when I come back and plug in a equals 0 here, and I'll plug in the fact that my initial velocity is just vx, right? So I'm just sort of relabeling this term using what I got right here. It leaves me with this. And so effectively what this means is that if I have constant velocity motion, effectively there's just one equation. I just have position as a function of time. It's going to be the initial position plus velocity times time. And so again, this is true as a vector equation, which again means that I've got one equation per dimension. So if I've got constant velocity motion in the x direction, there's my equation. Constant velocity motion in the y direction, there's the equation. Constant velocity motion in the z direction, there's the equation. So one of the things that we'll end up doing as we go through and work these kinematic problems is we're going to actually start by saying in each direction, right? So in each dimension that I need to worry about in the problem, do I have constant acceleration? Do I have constant velocity motion? So we're going to start by seeing which equations are valid for each dimension in the problem.